everyone. Hope the remaining participants will join in some part of some time later. Okay, so in this session, morning we have seen this 3D data visualization. Just for a minute recall, what and all we have used is we have used the library of RGL. We have used the library called Scatterplot 3D. Okay, ggplot2. So we try to visualize the data in terms of scatterplot 3D scatterplot, different types of a box plot, and we have seen one of the important function called ggpace, which gave us around 5 to 6 varieties of graphs in one strip chart. Okay, so that was more informative. But apart from that, if you want separate density plots, then you have a Q plot. If you want separate 3D plots, you have scatter plot 3D, and different, basing on the requirement, you have multiple functions available in R. And also we have seen and we have witnessed, we have listed some varieties of R packages available like RCMDR, Plot 3D, ggplot2, ggalley, okay, EasyGplot, ggcorpplot, like this. Okay, now with this basic introduction of the exploratory data analysis, now we move little ahead, going with the inferential statistics. So most of you might have read many textbooks, and we have come across that entire theory of statistics is divided into two. One will describe the data, one will help us to the methods, statistical methods and measures which are available. One part of the statistics will help us to describe the data, that is what we have seen in the last 2.5 days. Now hereafter, what we are trying to understand is the other, we are trying to make use of the other part of the data, other part of the statistical methods, that is what we call inferential statistics. But there is a bridge between this descriptive statistics and inferential statistics. Whatever the conclusion, inference is nothing but drawing proper conclusions out of the data with the help of the data. Okay, whatever the conclusions we make, again we have to fall back to the descriptive statistics, because the inferences or the decisions or the statements, what concluding remarks, what we are about to give should be based upon the mean and standard deviation on an average, because we'll come to see in next 5 to 6 minutes that how to define a null hypothesis, on what measure the null hypothesis will get defined. Okay, so like this, descriptive statistics are part and parcel of the inferential statistics to provide necessary two important things, that is what we call point estimate and interval estimate. Okay, in statistical inference, point estimation and interval estimation are the key concepts to deal with hypothesis testing framework. Point estimation is nothing but single point of value, that given a data, okay, given a data, I will compute mean, I will compute standard deviation, I will compute median. But will that be reliable enough, or will that be sufficient to explain about your data behavior? So point estimates may not be that supportive in a general context. Suppose if I repeat the experiment, I want to see the variability observed in the data. That variability should be accounted. That's why we take the support of interval estimation. That means when we have the mean, along with the mean, we need to have the dispersion of the mean, that is standard error of the mean, towards left side and towards right side. Okay, that we'll understand better with a graph. Okay, now I'm able to share my screen. We'll start with this. Yeah, what we're going to discuss is this. So today we are going to discuss, in this session, we are going to discuss about, sorry. I'm using the same PPT as a continuation. Yeah. Now, we are about to discuss about this framework. Okay, there was a question during the first day that when to use which statistic. That also we will discuss today. The total framework of hypothesis testing depends upon the parameters and number of samples you have taken. Along with that, two other important things is the significance level at which you test your hypothesis. Okay, that is more important. Now, all these notation, this is H naught is called in general. Okay, let me make simple like this. In general, when you conduct any experiment, you will have an objective. Sometimes an objective may become the null hypothesis, or sometimes it can be defined as an alternative hypothesis. First of all, we should understand the hypothesis. What do you mean by hypothesis? Hypothesis is nothing but statement about the problem, population parameters about the problem, on which you wish to compare two groups, compare several groups, or compare single groups. If you understand population parameters of which under comparison, it is nothing but here in one sample, okay, in one sample, I'll make it like this. Okay, in one sample, let me make like this. Okay, I'll take an example to make you better understand of one sample, two sample, and how you define H equal to mu naught, mu one, mu equal to mu naught, all these things. Okay, we'll start with an example that a limnologist obtained 8 containers of water from ponds. Okay, the pH level of each water sample was measured. So these are all the pH levels. So these particular 8 samples pertain to pond 1. Now, he says that generally the pH level should be less than or equal to 8. If I'm wrong, sorry. Okay, it should be less than or equal to 8. So if I take that the standard reference value was the population parameter mu naught, then these are all the randomly picked water samples from where the limnologist has measured the pH values in these randomly picked water samples. Now, the hypothesis of the limnologist is to verify, objective of the limnologist is to verify whether the pond 1 is meeting the standards of the pH levels, I mean less concentration of the pH levels. Okay, normal levels of the concentration of pH levels. Now, this question, this experimentation leads to a question that a verification that he wants to verify whether the pond 1 possesses to the normal concentration of the pH values or not. Okay, what is the normal concentration? Let us take pH is equal to 8. Okay, right? Now, the thing is, that will become the total general, whatever the water content you take, the pH level should not be highly concentrated. If not, it will create some problem, right? So here the point is how to define hypothesis for this problem. The null hypothesis will become mu. Mu is nothing but the sample, I mean the population parameter. Generally, the hypothesis will be defined in terms of population parameters. What is population parameter? Mu, sigma, okay, all these things are a population parameter, and sample measures are called x bar and s. Okay, small s. Okay, now in hypothesis, we need to define the hypothesis in terms of population parameters, that mu naught will become 8 and my mu will become the x bar, that is unbiased. X bar is the unbiased estimate of the population parameter mu. Okay, when we have this, the null hypothesis is mu equal to mu naught. Okay, the alternative hypothesis is mu not equal to mu naught. Okay, this kind of a definition, okay, this kind of a definition, it comes here. So this is my mu. Mu is defined in terms of a sample values, that is x bar is equal to mu naught. Mu naught is 8 to me. Okay, I am trying to verify this. I am equaling that yes, the samples which are collected from pond possesses the average pH value. That is I am going to verify in H naught. I am going to define in H naught. Alternatively, the composite, the contradictory part of this null should be defined in alternative hypothesis. Here, we are choosing one operator here, symbol, that is not equal to, which means that suppose if we define the pH level should be less than or equal to 8, then that will become one-tailed test. Okay, your area will be only one portion of verification. That is, if but in this example, here it is mu not equal to mu naught. That is nothing but your two-tailed test. Okay, tails are this. Now, when we say this is the mu, x bar is equal to mu. Okay, and we are defining that mu equal to mu naught. The sample statistic will be equal to the population parameter what we have taken. Okay, when we say mu not equal to mu naught, okay, then two regions of rejection will get defined. Two regions of rejection will get defined. Suppose if I say pH level, I mean average mu naught should be less than mu less than 8, then we get one left side region, one tail test only, one region, and this region will get for the rejection region, and this region is called acceptance region. So likewise, basing on if we know well in advance some information about the conditions of the parameters, then we can define mu less than or equal to mu naught, or mu greater than or equal to mu naught, or mu less than, mu greater than. All possible combinations of inequality parameters, inequality conditions can be taken into consideration, provided if you have some prior information about your parameter or variable under testing. Okay. Now, if you don't have that parameter, then leave it as a not equal to. Then what will happen? It will create two-sided region. Okay, that is what we call two-tailed test. Fine. Now, yeah, at this particular, where is that example? Where we'll go to that example? Yeah. Now, when we have one sample at hand, when we have one sample at hand and we want to have the verification whether these samples are relating to the standard pH value or not, then we have to use one sample t-test. One sample t-test, that is non-parametric analog is Wilcoxon test. Okay, let us consider I have collected this data, the limnologist collected data of these samples from 2 ponds. Let us take pond 1 and pond 2. Now, here, the objective will become whether the pH level, the pH concentration is equal in both ponds, or which pond has highest pH concentration when compared to the other pond. So the hypothesis will become the average pH value of P1 or pond 1 is equal to average pH value of P2, pond 2. That is mu1 equal to mu2. That will become null hypothesis. Null hypothesis is nothing but nullifying the differences existing even with known and unknown information. Okay. Now, we define mu1 as the average pH concentration of pond 1, mu2 as average pH concentration of pond 2. Now, the null hypothesis is mu1 equal to mu2. Suppose here also alternative comes as mu1 not equal to mu2, means that at least there is a chance that the pH concentration, the average pH concentration might vary between pond 1 and pond 2. Okay, suppose if I know the pH level of pond 2 will be more than 8, then I can define that average pH level of 0.1, that is mu1 less than mu2, then it will become one tail test. Okay, left side of the region will get generated and only the critical region will be on one side for possible rejection of null hypothesis. Okay, either way case, if I know prior information that pH levels of pond 1 are little higher than pond 2, then I can define mu1 greater than mu2. But most of the time we go with not equal to operator. But in most of the medical statistics and epidemiology studies, we define the one-tail test scenario. One-tail test scenario. Then when we have two independent populations, this is called single population. Now we have two populations here. Pond 1, the samples, water samples pertaining to pond 1 is one particular independent group, Pond 2 is another independent group. In order to compare the average concentration, pH concentrations of pond 1 and pond 2, you need to use two sample t-tests in a parametric way. If the assumptions of normality are not met, then you have to use Mann-Whitney U-test. Okay? I repeat again, whenever the single population is there, the parametric test is one sample t-test. The non-parametric test is Wilcoxon test. Now, when we have two independent populations, okay, we have to use two sample t-test and Mann-Whitney U-test. I will take the assumptions when we start writing the R code and how to interpret the outcomes. Okay. Now, if I collect more than two, if I collect more pH samples from more than 2 ponds, then if I take like this, I have a data of pond 1, pond 2, pond 3, pond 4. From 4 different independent ponds, okay, from 4 independent ponds, I have collected the pH concentration levels. Now, can I apply two sample t-test here? Someone may say yes. Why can't we apply? Simple, repeat pond 1, pond 2, pond 1, pond 3, pond 1, pond 4, and then pond 2, pond 3, all pairwise comparison. 4 at a time, 2 groups are at comparison, 4C2, 6 independent sample t-tests you have to take. But who will account for the variability across the groups and within the groups? Among the group and within the group, variability should be taken into consideration. Okay, the same question will come here. Okay, and that can be dealt simply because it is a two independent groups. The variance assumption will get verified automatically. Okay, but here, when we have more than two groups, two independent groups, here 4 independent ponds are there. Okay, we have to account for the variability, and moreover, the acceptance region should be defined upon basing on the mean values of each independent group. Okay, here the null hypothesis will become the average concentration of average pH concentration in all the groups are similar. We should not write same, similar, because the average value of one independent group will not be equal as same as the average value of the second independent group. Okay, so that's why the average pH concentration we should write, because on what measure you are trying to compare the independent groups is very, very important. Okay, the average pH concentration across 4 different ponds is similar. What about the alternative hypothesis? Can I write mu1 not equal to mu2 not equal to mu3 not equal to mu2 mu4 not equal to? No, that is not the right way to write. Right way to define the alternative hypothesis. You should write at least a pair of ponds do differ. At least a pair of ponds differ on an average pH concentration. Why we have to write like that? Okay, there is a chance mechanism totally that the average value of pond 1 may be differing with pond 3, but these two might be same. At the same time, there is all 6 alternatives are there. Out of the 6 alternatives, at least a pair do have a different average pH concentration level. So the general notation comes with mu I not equal to mu j, I not equal to j. Ij is nothing but 1, 2, 3, 4. Pond 1, pond 2, pond 3, pond 4. Now, when we have this kind of a scenario, more than 2 independent populations to be compared with respect to mean. With respect to mean, we have to use one-way ANOVA or Kruskal Wallis H test. This is a parametric form and this is a non-parametric form, non-parametric test. Now, why have used a one-way factor here, one-way label? Because my concentration of observing the variation or the average difference across the ponds, the pH levels are collected from 4 independent ponds. My factor is 4 independent ponds. Okay, suppose if I add from region 1, region 2, region 3, then what it will become? I have to observe the variation of pH concentration across regions as well as across independent ponds. Regions are independent, ponds are independent. Then this will become the factors that are helping us to explain the variability across the regions, across the ponds with respect to mean. With respect to mean is called two-way analysis of variance. Okay, like this, as you increase your experimental design, the statistical method that you imply there will change according to your study design. Okay, according to your study design. Now, yeah, so one along, I hope with this it is clear. Now, we'll come up with the assumptions here. R code is single line, it won't take much time, okay? But I want to make it very clear that why we have to go with the two sample t-test, when we have to go with the two sample t-test, how to conduct two sample t-test, okay? Now, we are taking the assumptions part of every test here. Non-parametric, most of the time we don't believe on assumptions because they are independent of parameters, okay? All the non-parametric, I want to make a note here that all the non-parametric tests work on a rank-based phenomenon. Okay, each observation will be ranked, clubbed together, and then divided according to the groups, and then ranks will be summed up, and accordingly the statistics will be computed and p-value will be computed. So that is out of the discussion as of now. Okay, but we focus on the non-parametric test. What are the assumptions that each parametric test, like one sample t-test, two sample t-test, and one Way Anova has? The common assumptions are that the samples are normally distributed. The samples are normally distributed. Okay, how to check the normality assumption? You can do Shapiro-Wilk test, then you can check the normality. Using the Shapiro-Wilk test, you can check the normality assumption. If the normality assumption fails, then what to do? Choose the analog of non-parametric, that is non-parametric test. For two, suppose if you are checking the normality of pond 1 and pond 2, then if it fails the normality assumption, better to go with the Mann-Whitney test. Then represent the data in terms of median and interquartile range. Then you can you can draw conclusions according to that. Now, what is the very blind way, very thumb rule way of observing the means and the normality? It's nothing but mean and standard deviation. The standard deviation should be as much as smaller when compared to the mean. It should not be nearer to the mean value. Okay, there is an indication mean plus or minus 2 into standard deviation, plus or minus 2 into standard deviation. Then that as the standard deviation closer to the mean value, it indicates that too many samples are scattered from the center. That is one assumption. Second assumption is homogeneity of variances. Homogeneity of variances. From one sample t-test to two sample to ANOVA, this homogeneity of variance test is also to be verified. Okay, but most often we entertain to have the variability so that we can have a significant p-value. Okay, now what is homogeneity of variance here? Sigma equal to sigma naught. Sigma square is equal to sigma naught square. How to do? We use chi-square test for homogeneity of variance, that is ns square by sigma square. Okay, how to test? Here the hypothesis will be sigma 1 square. The variance observed, the variability observed in pond 1 is equal to the variation of the pond 2. That is h naught is sigma 1 square is equal to sigma 2 square. How to test that assumption of variances? You use Levin's F test. Okay, using Levin's F test, you can test the assumption of variances, whether they are equal or not. But most of the time we conduct the t-test assuming equal variances. Okay, now when we extend two independent groups to more than two independent groups, then no more this Levin's F test will come, but we come across another statistic to compare the variances across k groups. across K groups is Bartlett's test. B-R-T-E, Bartlett, B-R-T-L-E-T-T-S, Bartlett's test, which will have the hypothesis that sigma 1 square is equal to sigma 2 square is equal to sigma 3 square is equal to sigma 4 square. Alternative is nothing but sigma I square not equal to sigma j square. Okay, at least there also at least a pair of groups have the homogeneity of variances. Okay, so like this, the background of parametric test has a lot of statistical flavor, that one with normality assumption, the group should be independent. Okay, the samples are to be collected at random. Okay, and then the homogeneity of variances. So after having all this framework of hypothesis testing, then the choice of statistical technique will come basing on the number of independent groups available in your experiment. Okay, fine. Now, what we do is we will understand, uh, yeah, we will understand the p-value framework. Whatever the value, first of all, we do hypothesis testing for possible rejection of null hypothesis in order to show, indirectly to show that there exists some novel thing that you have observed in your experiment, Okay, now when we say this 3 sigma limits, the dashed area is called rejection region, and the area which is nearer to the mean and left hand side of the mean is called acceptance region. Now, earlier I have in a couple of a few minutes ago, I have used the terms called interval estimate and point estimate. This is called interval estimate, a single point value, which will talk about that where the data tends to lie. But will that be same always? Will that be same always? Not necessarily, because the samples are random or having natural variability. So the point estimate will not be always the same, will not tend to lie at the same central value. Hence, we need to take the account of variation of the natural variability so that we can define lower confidence interval and upper confidence interval. So this lower and upper confidence interval will give us the boundary region of this average value. Average value, that is what we call mu cap, or mu plus or minus, or x bar plus or minus standard z alpha, standard error of x bar. The standard error is nothing but the variability accounted by the random samples collected in the data, that are observed in the data. So this is 5% level or 1%. The tails will get divided. 0.05 by 2 is 0.025 on both left and right side of the things. Okay. Now, what if the p-value is beyond this, within this region of dashed line, then it clearly indicates that there is some kind of a chance mechanism that two groups are differing to each other and they have a different means. Okay, they have a different means. Okay, now what is, because most of the time we are fascinated to hear the word called significance. What is the significance of significance? Is nothing but p-value. Okay, what is the significance of significance? We have to understand statistically that if we observe a p-value which is less than the specified level of significance, that means the natural variability observed in two independent groups has something to tell that they differ to each other. Okay, now the next thing is, most of the time we call that most of the time, which denotes the p-value, that probability of being mistaken when we reject the null hypothesis. The closer the p-value to 0, the more certain we can be of not rejecting a true null hypothesis and when accepting our own alternative hypothesis. There will be some instances where you get 0.00000. Okay, what does it mean? Let us take, for instance, you take 0.03. Okay, my alpha level is 0.05. So when you have an experimentation of such kind for 100 times, 3 times you will be having a chance to commit a mistake of accepting the null hypothesis, even though it has to be rejected. Okay, 3 out of 100. When there is 0.00, as smaller the p-value, there is a high certainty that definitely your hypothesis, I mean the decision about the inference what you draw out of this experiment will be certain to accept the alternative rather than the null hypothesis. So the most thing is, most of us or most of you, most of the researchers define a null hypothesis that H naught, the average, they will define like this is the mistake we should not do. The pH values of pond 1 and pond 2 differ significantly. When you know well in advance that they differ significantly, significantly is very sensitive word to be used. Okay, when you are claiming that differs significantly with a confident, that is not the way to write. You have to write, you have to take the statement in such a way that using which measure you are comparing the groups of your experiment, that has to be prescribed very properly. The average pH concentrations of pond 1 and pond 2 differ, that's it, differ to each other. Statistical word should, a significant word should not be entertained. That should be entertained at the end of your, during the interpretation part, reporting part, because you have an evidence to claim that the difference is significant enough to claim that the average pH level of pond 1 totally different with P2, pond 2. Okay, when you have a certain evidence, okay, evidence-based medicine, you might have heard like this. The statistics also provide some kind of evidence-based mechanism to conclude your objectives with the proper remarks using these p-values. Okay, but that's what we said. Confidence intervals are very, very, very important. Other way to tell is it is a scale of potential uncertainty. Okay, the potential uncertainty. So what is uncertainty? The estimate may be within the lower and upper, but potentially I can tell that the mean value of the pH will be within that particular interval. So potentially we can have the estimate within that interval estimation, the point estimate within that interval estimation, but I'm not sure which value it will take because of natural variability of the sample, experiment by experiment. Okay, now this is what we have seen now. I'll do one thing. Now we'll switch over to the coding part slowly, where we have, yeah. Okay, we have, I have taken one more example also, like what is the time taken for germination time of these pine seeds. When we have an greenhouse kind of a production and outside thing. So this is a germination time. Here the experimental question is whether the germination time will be same or similar of germination time of pine seeds will be same when we have a greenhouse kind of a environment or outside environment. So this is to be verified. How to define the null hypothesis here? The average germination time of greenhouse is equal to the average germination time of outside mechanism. Okay. Then alternatively, what will happen is the mu1, mu g, we can write as a greenhouse as g, mu g not equal to mu o. Okay, now enter the data and then apply the R code to sample.test and then verify with the p-value. Simple. Now, this is another example what I have discussed it now. Okay, this is pond 1, pond 2, pond 3, pond 4. These are the pH levels, and then we'll start understanding the R code for this. Okay, R code for this. Okay, now I am using two different data sets here. One is LBW data, where I want to verify the average, the standard value of the healthy weight, healthy babies, that they say that baby should weigh 2.5 kilos. This is a point estimate. But is always okay with the 2.5 kilos? No, 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 not required. 2.2 to 2.8 above, upper ceiling, 2.8 above, 2.2 above, okay, or 2.5 above. So I can define that mu greater than 2.5, okay. So here I want to test the baby's weight where the population value should be 2.5 kilos, that is 2,500 grams. But I say that these values should be greater than 2,500. Let me test whether the baby's weight, which is observed in this particular sample of data, is satisfying the condition that mu greater than mu naught. Mu greater than mu naught. This mu naught is 2.5 kilos and mu is obtained from the data. That is nothing but your X bar sample mean. Okay, here in this particular study, we are very clear that for a healthy baby, the weight should be greater than, it should satisfy this condition. This is one-sided test. Alternative is greater. If you don't have the information, alternative is two-sided. Okay, so T dot test is very simple function to be used. It doesn't require any package. Once you install R, all these functions are inbuilt. Okay, all these functions are inbuilt. T dot test, the variable under comparison, the population parameter that is to be used for computation, and alternative hypothesis. If it is two-sided, you should write two dot-sided. If it is greater, you have to write greater within double quotation. If it is less than, you have to write less. You have to write less. So these three arguments you have to remember. T dot test, variable name for comparison, the population parameter, and the alternative hypothesis. Either it should be two-sided. Suppose if you won't give alternative, just T dot test BWT comma mu equal to 2,500, close the parenthesis. By default, it will assume two-sided test. Okay. Alternative, suppose if you have some information that no, baby's birth weight should satisfy, the sample should be more than 2,500, then you should use an alternative argument as greater. Okay. Now, I'm using another, yeah. Now, from the same data set, I have two set of populations of women. So two subpopulations of women. What is that? Low birth weight, smoking and non-smoking. And this is your mother's weight. Okay, I have a very rough objective, very rough objective. I want to see whether the smoking, will there be any weight difference between the smoking mothers and non-smoking mothers. I want to validate this statement that, or other way I can claim that the mothers, the women who have the smoking habit, their weight will be lesser than compared to the non-smokers. This is my statement. So then it will become two independent the total 189 samples get divided into two things. What is that? Smokers and non-smokers. They are exclusive, right? The mothers who belong to non-smoker, they may not come in the group of smoking, and smoking may not come to the group of non-smoking. So then this variable that has to be compared across the factor variable, then first variable should be defined, then modulo operator should be used, and the category factor variables that are to be where this variable to be compared should be defined, and you have to call the data LBD, and I'm making an assumption that var dot equal variance dot equal is equal to true. I'm making an assumption that variance dot equal to true. Here I can add one more argument called alternative is equal to what is this? Yeah, two dot sided. Okay, so an alternative statement I can make here, one more argument. But if I don't give that, then automatically it will assume that it is a two-sided test. Okay, now another data is there, sleep smoke data, the sleeping time for the smokers. Okay, sleeping time is this continuous variable, and smoking is a factor variable. Data is stored in sleep, variance dot equal. Here, another alternative line of R code is written in such a way that, assuming that the people who do not smoke have a longer, on an average, they have a longer sleeping time than the smokers. So their sleeping time will be less than the non-smokers. So the first group is smokers, the second group is non-smokers. So I can tell as less alternative statement as mu1 less than mu2. Okay, so this is what we do. Now let me complete the ANOVA. Let me complete the code and then we will do that. Okay. Or let me do one thing. Let me complete this T test and then we'll go with ANOVA. Is that fine? Where is my R studio? Yeah. Okay, let me load the data. Okay, now attaching T-test. See, now what is the value we got? Just with the click of a button, it will tell the data variable which is under consideration. This is the T statistic value. What is the T statistic mathematical formula behind? The X bar minus mu naught, okay? X bar minus mu naught into root n by S, okay? Distributed according to Tn minus 1. So n minus 1 is 188. P value is 1.227 e to the raised to the power of minus 14. It is very least 0.0000. Now, since I have taken two-sided test, the value population parameter mean value is 2.5, the 2,500 grams. Okay, the mean observed from the data is 2,944.286 grams, which is quite on the upper side of the 2,500, quite on the upper side of the 2,500. But what is the this is the point estimate of the data. What about the interval estimate? This is the interval estimate. See, this is the interval estimate of the data where the average birth weight of the baby in this particular data ranges from 2,839.67 to 3,048. Okay, to 3,048. Whereas we are rejecting the null hypothesis that the average baby's weight which is observed is not equal to 2.5, it is above 2.5, and the difference is called the mean effect, the effect size. Difference of what? 2944 minus 2500 is the effect size which is observed from the natural variability of the samples which we have in the low birth weight data, indicating that the average birth weight of the babies is higher than the standard code. So in general, taking that as a complete 189 samples as one population, all the total sample indicates that the baby's birth weight are meeting these standards. Okay. Now, if I change a little that the alternative should be greater, then what I get is the p-value will get changed, because now here what will happen? The region will get only one-sided, greater than, only one side, the right side of the normal curve will get activated, and according to that the p-value will be computed. Here also still we are rejecting only, but you see the lower confidence interval is 2856, but the upper confidence interval is infinity, because when you see the PowerPoint, the dashed line, that is the vertical line, right? From that point to infinity, that is the region of rejection. So the mean will start on an average with the 2856, the left side interval, and it will go as much as possible. So this is one tail test. And the decision what we take is, yes, the average birth weight of the baby is not equal to, is greater than, here not equal to, is definitely greater than the standard value. Okay. Now we'll go with two sample t-test. Okay. I'm using mother's weight with the two populations of, okay, we'll do with from 2 to 3 days we are using low birth weight data only. We'll go with some other data, sleep smoke data. Okay, you can see this sleep smoke data here. Okay, see, this is the smoker group and this is non-smokers group. Sleeping time. Okay, sleeping time, this is in minutes, in minutes. Okay, 69.3 something. Okay, now when we do that, assuming the variance equal to 2, I get this. Okay, now how to understand this output? The first thing is, first you have to, don't look at the p-value. The first thing is you have to look at the mean values. Okay, the average sleeping time of non-smokers is 30.32. Okay, average sleeping time of smokers is 43.47, comparatively at higher level. Okay, comparatively at the higher level, and come to the confidence interval. Okay, what is this? It is different, right? Now this confidence interval will get built upon this value. This value. So this is nothing but the difference in t-test. What is the formula in the numerator? Mu x bar, x1 bar minus x2 bar, right? That difference is called effect size. Okay, the negative symbol or positive symbol will get reflected in t. Okay, and the denominator is standard error. Almost we are standardizing the numerator part with the variability observed clubbing the two populations. Okay, clubbing the two populations. So this will tell the confidence interval for the effect size. Okay, effect size. So minus 2.771 is nothing but the average sleeping time of non-smokers is quite less than the smokers, quite less than the smokers. Now, with the knowledge that definitely smoking people with a drowsiness or different thing, they sleep more. Okay, then when we do that, the hypothesis, since it is less, okay, I have taken less, the left side of the region will come, that is minus infinity to the mean effect size. Okay, that's why minus infinity to minus 5.156. Okay, but now your question might be, I'm guessing that what should be reported in the what was the presentation, what you wish to do. What you have to report is, first you have to report the mean and standard deviation value of this. Next, you have to report the t-test values. This you have to take as a support to write the reporting. No need to present. Okay, okay, no need to present. So this is how we do with independent sample t-test and single one sample t-test. We'll go little ahead. We'll go little ahead in taking the data of Way Anova. Okay, I'm using the bone strength measured across different age groups, young age group, okay, middle age group, and elder age group. Let us take, like, I think in the study they have given adolescents only. Let us take 15 to 25 as a young age group, 25 to 45 middle age group, and 45 above are elder age group. And they have measured this bone mineral density, bone strength, in these three age groups. Now, three groups of age are independent to each other. The factor is age. Okay, the factor is age. Now, what we can say is, we cannot use two test here because it has the data has three age groups. Then we have to go with Way Anova. Okay, I'm reading the file here. And then AOV is nothing but analysis of variance. Okay, AOV is nothing but analysis of variance. The variable under to be compared across the groups. Data is stored in OW, that is Way Anova. I mean, OW is, I have written like that. Summary of OW result. OWRE is nothing but Way result. Okay. And then aggregate is, again, I'm using a function aggregate here to display the mean and standard deviation of bone strength across each group. Okay, the same function can be used here also. Okay, let me do this. Okay, you can view this data here. So young age group, bone strength, middle-aged group, and elderly group. So this is the data. Okay, now we will conduct the one-way analysis of variance. Okay, it is executed, and then summary. This is the ANOVA table what I get. Okay, what does ANOVA table contain? The source of variation at which where you want to observe the variability across the groups and within the groups. Within the groups is residuals, and degrees of freedom is that what is the weightage? How many samples to be weighted? Okay, to be given freedom of weightage to have the to define the p-value. Okay, and sum of squares across the groups, that is between the groups and within the group. Okay, and this is the p-value 0.0009. Now what is the null hypothesis here? The average bone strength of young group is equal to the average bone strength of middle-aged is equal to the average bone strength of elderly group. Alternative, mu I not equal to mu j. Now, with this p-value, we conclude a statement. We conclude a statement that the null hypothesis has to be rejected in the sense to accept the information that the average bone strength do differ, average bone strength do differ across the three independent age groups. Now, next thing will come. What are the average bone strength levels in each group? Let us see. The average bone strength of elderly is 70.07. Middle age is around 100. Young age is around 118.2. That's good. But the next question will rise. What is the next question? It is fine that we have rejected the null hypothesis and we have accepted the alternative stating that at least a pair of age groups differ with respect to the bone strength. Now we need to find out which pair of age groups are having that true statistical difference. Okay, for which you need a pairwise comparison. Okay, you need a pairwise comparison. That is what we call post hoc test. Post hoc is nothing but once the ANOVA is executed, you need to and significant p-value is observed, you need to check for further investigation that which pair of groups are having similar average values of bone strength and which groups differ with respect to the bone strength on an average, for which I use a function called pairwise.t.test. Okay, pairwise.t.test is the function. Pairwise is nothing but young age group versus middle age, young age group versus elderly, middle age group versus elderly. Here, what are the arguments to be defined is variable that is to be compared across each pair, and the G corresponds to the grouping variable, and I'm using one for any test. I'm using one for any test as one of the post hoc comparison. Running this, I get this kind of a table. Okay. Now here, three multiple hypotheses will get splitted. Will get generated. What are the three multiple hypotheses? The average bone strength of younger age group is equal to the average bone strength of middle aged. Second hypothesis, average bone strength of younger one is equal to the average bone strength of elder one. Third hypothesis, the average bone strength of middle aged is equal to the average bone strength of the elderly group. So these three hypotheses will get defined because we have testing the bone strength across three pairs after observing the significance in ANOVA. Okay. Now, here the p-value is 0.04. We will be so happy. Yes, it is rejected, but we should be very careful. We should be very careful in a sense that what is that? Sorry. The total significance level we have taken for testing ANOVA is 0.05. When we do the pairwise comparison, the same level of significance should not be considered. It should be divided by the number of groups at comparison. That is what, if we don't do that, what I mean to say is 0.05 by 3. Okay, what it will come? 0.0133. So this 0.0133 will become the level of significance for each pairwise. So if we don't do that, we are creating an error rate. That is what we call family-wise error rate. But most of the research articles, what they do is they will consider continuing 0.05 even for post-hoc comparison, and then start middle-age group significantly differs with elderly group. So the bone strength is of middle-age group is not equal to the elderly group. That is not correct. The family-wise error rate should be taken into consideration in the mean. That what is the mean value here of middle-aged group? 100, and elderly group is 70. The difference of this 30 or 29 point something is not that significant. It's not that noticeable difference, that middle-aged, the bone strength, average bone strength of middle-aged and elderly are not that, it's not that noticeable difference. Okay. Now, whereas young versus elderly, this is 70 and 118, around 38. Okay, the p-value is 0.0007. This clearly notify that 0.0007 when compared to that divided alpha rate, that is 0.0133, signifies that yes, there is a true difference, mean difference exists between the elderly and young age group with respect to bone strength. How to conclude is, the younger group have higher bone strength levels than the elderly group. Coming to the young group and middle-aged group, what we do here, younger group, they are very close by. So more or less, the average bone strength of younger age group and middle-aged group are more or less similar. So there is no difference. So that's why this is the main purpose of conducting post-hoc comparison. Okay, so with this, I stop the discussion. Now I'll give 5 to 6 minutes for any queries that are to be answered, that has to be answered in this particular thing. I have one more topic to that topic to cover. That is what we call two-way ANOVA, that I'll cover tomorrow morning, and then we'll go with the simple correlation and regression. Okay. Do you have any questions in this? And I sincerely request if any researchers, any faculties are available, are observing this particular discussion, I make a point here that family-wise error rate should be considered in research publications. You should compare the p-values using that family-wise error rate. And you have to provide the confidence intervals for the final summary statistics, right? Okay, family-wise error rate is the thing that, suppose I have chosen level of significance as 0.05. Okay, in the present data, what we have taken in bone strength, okay, in bone strength is that three groups are there. So 0.05 should be divided with the three groups. Then the p-value per pairwise comparison is 0.013. Thereby, you are restricting the level of significance of type to reduce the type 1 error particularly. Okay, you are controlling the level of significance pertaining to that particular pair. So that is what we call family-wise error rate. If the p-value of the test is nearer to 0. See, if I suppose, so for instance, if we take 0.047, still we interpret that numerically 0.047 is less than 0.05. Okay, then we have to reject the null hypothesis. But that difference, that's what I said. The effect size or the significant p-value is purely due to chance of natural variability in the data. Okay, and with that p-value only, we have to draw the conclusion. Okay, and then what is the next question? What is degrees of freedom? So degrees of freedom, let us take n observations are there. Okay, 189, let us take around 30 observations are there in the data. Okay, degrees of freedom, we say n minus 1. Why we take n minus 1? When it comes to two independent sample t-test, we write n1 minus 1 plus n2 minus 1. 2 degrees of freedom will be lost. I mean, two samples will, n1 plus n2 minus 2 we write. There is a general understanding that in statistical, the experiment should be conducted in identical and independently identically distributed samples. Okay, even in most of the life sciences and medical sciences experiments, you do the experimentation with a homogeneous environment. If not, the variability will get influenced and the measurements will be totally out of your control. So when you have this identical measurements, identical samples that are collected at random, okay, in most of the clinical trials, this happens like this. You have 30 people in one group and 25 people in another group. You have taken drug A and drug B. They are all homogeneous, identical tints, same concentration of drug is given. Okay, right? You have two different trays, one tray for drug A and one tray for drug B. By that time, you might have labeled which patient should be given drug A, drug B. This is a big permitted block randomization technique that comes in clinical trials. Different randomization techniques are there. I'm giving the overall understanding that how it is degrees of freedom. Now, if I start issuing the drugs to the drug A group, okay, even though still it is homogeneous, the first patient has the weightage of 25 tens, 25 small tens, okay, and so on and so forth. When you start going issuing the drugs to the 25, in the last but one, 24th the patient also has some sort of a freedom to take either of, even though they are homogeneous, there is a chance to take that out of the two tens, I can select one. But the last one has lost the freedom that whatever is left out, which is homogeneous or anything, that he has to take. So out of n samples, one sample, one individual will lose the degrees of freedom. The weightage of being issued a particular treatment or a experimental protocol will be lost for one individual in every group. That's why in ANOVA, it is called n minus k. Number of groups at comparison, number of samples, n minus k is the degrees of freedom. Okay, I hope I have cleared that. My email ID, 1 minute. I have already given. Anyway, we are statsguru@gmail.com. Okay. Any more questions we have? Okay, there is some question like estimations of R coding. Okay, I'll try to cover because we have some other topics to cover. I'll try to manage the time. I'm focusing more on interpretation and understanding the observations because that is the training what we need to give. Least significant different test, what I, to the best of my knowledge, what I read is it has, one for any test has minimum type 1 error rather than least significant difference test. Okay, so that's why we prefer Tucky or Bonferroni. Okay. No, this n of k minus 1 may be related to some other thing, not ANOVA. I don't think so. Real interesting session, but due to unavailable situation, okay, the college people, I think they will be they will be sharing all the they'll be sharing all the videos with you, with everyone. F calculated 20 point. F calculated is a manual calculation. That's nothing but mean square. Sum of squares, mean sum of squares due to groups. age groups divided by mean sum of squares due to error will give us that F value. But this F value is very, very important in computing the P value, because the distribution is F, a little complicated, but I'll try to make you understand that the P value of every test statistic will be computed like this. P value is equal to integral x to infinity, that particular density function, of the distribution. Suppose in ANOVA, the density function is F distribution. X to infinity. X to infinity is nothing but you are defining that x to infinity is the critical region where you want to see whether the possible rejection of null hypothesis will be there or not. Okay, that x is nothing but your calculated value. So in this 20.58, 20.58 is nothing but 20.958 to infinity, the one-sided region. Okay, F distribution is a one-tailed distribution, right? Okay, so 20.58 to infinity, estimate the area using the F distribution, So that is a complicated where the programming, computational programming will take out at the backside. Okay, and finally we'll get that p-value. Simple example understanding that you can do this beauty in Excel. You calculate the same ANOVA in Excel. Okay, then what to do is you will get F value, you will get F inverse. There is two different things, F dist, F inverse. F dist will give p value, F inverse will revert back your statistic value. So Excel is very wonderful thing for all this, knowing that what will happen background. Okay, it is a probability value, that's what I said. It is the probability value of rejecting the null hypothesis using the functional form of the particular distribution or the test statistic. Standard error, which will tell the variability. Okay, sigma by root n. One sample test is nothing but sigma by root n. Means the standard deviation will be divided by the number of samples. Even in two sample t-test, the standard error is the combination of two samples, right? So that standard error will take the cumulative variability observed between the two independent sample, and that will tell us that will help us to define the confidence interval. See, in the process of defining p-value statistics, all this thing, F value you just present for reporting. The total conclusion interpretation should be taken using p-value. Okay. How to apply t-test when the data in two sheets? Madam, that comes with, when the data have two different sheets, you have to first create a data design. Okay, then only you can do all these things. Okay. How to read? Yeah, sorry, I forgot that. I will check that. I will check that. How to read two different sheets. Okay. Right. Then when we inverse F, then F should have to be continuous. Huh? F should be, F value is continuous only, no? If AC value is small and K is test and P value is greater than the other distribution, while comparing a set of distribution, what does it mean? Okay. Okay, if AC is small, AC is nothing but it's a measure of goodness of fit. Case is for testing normality. See, it's very clear. Why we test for case? One sample Kolmogorov-Smirnov test, whether the taken data has the distributional pattern of the distribution you are under comparison. Suppose if you are comparing exponential distribution, you have a skewed data. Okay, but apart from that, you suspect that the tail end distribution is like some beta or gamma. Okay, now the hypothesis will get that the sample values are distributed according to exponential. Okay, when the p-value is greater than 0.05, it indicates that the sample values are distributed according to exponential. Automatically, it shows that data should be of best fit. But still, if best fit and resulting that the data and the observed fit and true fit are more or less equal, resulting ASC value smaller. Hope I have made it clear. Okay. How far samples determination is important while conducting? Very, very, very important. Very, very important. That is a big theory behind that. Okay. And you have to tell the effect size. That will requires another session. That requires another session. In simple, I can say yes, definitely sample size should be defined well in advance before you do some statistical tests, or before you conduct any statistical. Before you conduct a study, the protocol should be equipped with statistical methodologies that are to be used in the post collection of data. The sample size, how you have arrived, what is the level of significance you are taking. Okay, how to read data in two different sheets. Madam, that's what I said. What I said is, suppose you have point 1 in one sheet, point 2 in one sheet, then it is not the way to do. You have to bring two groups of data into one particular sheet, create a data design appropriately, and then run the code. Okay. Suppose if you have one experiment in one sheet, another experiment of some other parameters like some other parameters, another sheet, how to read how to read Excel file when it has multiple sheets. Really, I don't know. Let me read it and tell you. Okay. Right. Yes, we can do different sample sizes. We can do. We can do. It is independent of even though it is unbalanced also, we can conduct this independent sample t-test. Only with the paid sample t-test, it should be of same sample size. Okay, fine. Right. If there are no questions, I think we can leave the, and tomorrow we will be discussing about dependent samples. Tomorrow I'll discuss, madam. Dependent samples should have the balanced samples before and after. Okay, right. Okay, thank you. So tomorrow morning we'll meet again. We'll meet again by 10:30 to discuss about paid sample and two-way ANOVA. Then we'll go with some simple regression correlation. Thank you.